Look, guys, we might just start the meeting then. Just to first off, welcome to everyone. I need to warn you, and you probably would have already seen it when you logged on. We are recording these sessions, and they will be available as MP3s, MP4s, I guess later on, some sort of video format from the Variable Stars South website. I don't think there's any plans to have them on a YouTube channel, but certainly through the website. So I ask you all to just be aware that the video will be recording sight and sound, so keep things appropriate. What else have we got? Just try and find my notes. A quick reminder, the session 1 and 2 have been on the Saturdays. Next weekend, we have to have our final session on Sunday, October 2nd, to avoid a scheduling clash with the Astronomical Association of Queensland, who have a meeting on the Saturday afternoon. So we're meeting on the Sunday. As an additional complication, Eastern Australia, other than Queensland, are going to be observing daylight savings then. So I'll send a reminder out exactly what universal time that will be. I think it's 1 AM UT, and I'll leave it to the individuals to work out what their local time is for that. As I said just now, welcome to all those who were here with us last week, and also for the new names. Great to see we have a good turn up so far. We may get 1 or 2 more. Today we have 4 presentations, 3 speakers, but 4 presentations. Each will be approximately 30 minutes long, and that includes a little bit of time for questions. During the talks, you can post questions to the, or comments for that matter, to the chat, using the chat facility in Zoom, but we might not get to address those until after the presentation. We don't want to break the continuity too much. So with that, I shall introduce our first speaker, Arne Henden, who is staying up late for us for this one. In his local time is just after 10 PM, I believe, on the northeast coast of the US. I'm sure most of you recognise Arne as a former AOVSO director for many years. He was certainly the director when I started my photometry exercises way back in about 2010, I think it was. He's now doing a lot of work still with AOVSO with the robotic telescope network they have around the world, and that's a fantastic facility, and hopefully will be expanded to even more facilities in other parts of the world. But prior to his AOVSO career, he had a long distinguished career in observational astronomy as well. So a warm welcome to Arne, and his talk today, if I can get the right piece of paper up, his talk today will be on the Nova that occurred back in 2002, since been named V838 Monoceros. I believe that's the pronunciation, I'm not too sure. So I'll hand over to Arne to give his presentation. Thank you.
Okay, well, thank you, Mark. It is kind of interesting to be giving a presentation to a group that's 10,000 miles away from you. Amazing what electrons will do these days. So what I want to talk about today is a star that I've followed for the past 20 years, off and on. There are about a dozen stars that have caught my interest over the decades. This is one of them, so I've followed it for 2 decades. There are a couple of other stars that, like Polaris and CECAS and QX Pup and things like that, that just there was something unique about them, and so they've held my interest. V838 Mon is a star that is at 7 hours right ascension, and so it's actually rising now in the early morning, and you can actually get to it. So it's one that for the next few months you actually can monitor and follow if you so feel. So the star itself went into outburst in January of 2002. Nick Brown, your fellow compatriot from Australia, was the one who discovered it. It increased in brightness from a quiescent magnitude of about 15 up to an outburst magnitude of about 6. One of the interesting things about it is that it had a spectral evolution that went from sort of a B star when it was in quiescence to an F star during outburst, and then towards the end of the outburst it actually got extremely red and turned into what is considered an L supergiant, one of the few known members of that class. It's also considered a prototype of a class of variables called the luminous red variables. There are probably half a dozen of these now that have been discovered. And one of the questions that always comes up is, well, what causes it? Why is it different from other novae? And it could be an example of a stellar merger, for example. The other question that comes up is, well, how far away is it? So how intrinsically bright is it? And so one of the things that was discovered by Howard Bond and a colleague was that there were other B stars nearby that looked like they might have been part of a young cluster, and perhaps V838 Mon's stars were part of that cluster. So that was a way of determining distance, nothing else. The other neat thing about this star, and I'm sure everybody is familiar with it, is that it has a light echo. And so it had one of the most spectacular light echoes that have ever been seen. And HST was able to follow it through its evolution. From various means, we figure that the distance is about 5.5, 5.6 kiloparsecs, so it's pretty darn far away. And because of the uniqueness of the star, it actually had its own symposium on La Palma in the Canaries in 2006. So lots of controversy, very unusual light curve, and so on. So let's get into the star. These are the discovery images that were taken at the U.S. Naval Observatory in Flagstaff. I was monitoring V838 Mon, and so these are the discovery images of the light echo. And so you can see in early January in the U-band, it looked pretty much like a normal star. And as time went by, it got larger and larger. And soon it was very obvious that it wasn't an artifact of the filter or the scene or something like that, but it was actually some structure around the star that was being illuminated. And we then sent out what was then an astronomical telegram announcing that this was the case, and all of a sudden all the professionals around the world said, this isn't just a standard nova, we've got to go and take a look at it. We also, right around this time in early April, why am I not doing this? Sorry. In early April, we were able to convince Hubble Space Telescope to take an image of this particular object. And it's really interesting with Hubble in that they don't like to take publicity photos. What you have to do is find some science that you can do with those photos before they will actually schedule them. And so the first one was actually done with director's discretionary time, and they just took an image for us, a very short blue band image. And then after that, we were able to convince them that we could do some work with the polarizing filters in the camera that had just been installed, the ACS, and determine distance by looking at polarization of the light echo. And so then they actually then started to take additional images of the light echo. And so that's the whole story of how HST started to observe this. They wouldn't have done it otherwise. So this was the first image that HST took. We had seen these sort of rings from the ground, but with HST, it was very obvious that you know, these things were showing up. And each one of these rings basically is a cloud of material that's between us and the star. And so just by light travel time, you get this kind of ring effect. And if you notice, here is V838 Mon itself, and there's this sort of arrow that points to the star. So it's a really easy field to identify. And I'll show you some of the ground-based photos then, and you can see these same stars. For instance, this one right here, the light echoes just sort of reached that star. Here's the best picture that I took with the 1.5 meter telescope at USNO in color. Now you can see that, yes, the nova itself is very red, and you can see the light echo off of the dust, both in the vicinity and in the foreground of the object itself. When you're looking at something like this, you're seeing a two-dimensional image of a three-dimensional object. And so it's difficult to identify what's in front, what's in back, what's close to the star, whatever. But now you can see that same kind of arrow pointing to the star. And before, this was the star that the HST's light echo had reached, and now you can see that the light echo is expanded by almost a factor of 2 beyond that. It's a very pretty field, and these are the blue stars that are part of that young cluster that Howard Bond and his colleague were saying that perhaps the progenitor of the nova was part of that young cluster. So here is the movie. All right. Am I not going to play it? There we go. And you can see these are images taken over about a 4-year span by HST in multiple colors. And you can see how the structure of the light echo changes over that period of time. The star itself looks like it's becoming yellow, but that's because it's just so saturated that Hubble has burned it out, and so you don't get a true color. And the main reason was that the light echo itself was getting fainter as it expanded, and so you had to take deeper exposures, which means that the nova itself is way overexposed. I took a lot of photometry of the star from USNO, and notice here on this light curve that the time scale is logarithmic. So the main purpose of that was to sort of expand the early time evolution of the nova and not worry about the sort of quiescence stuff that generally nothing is going on. You're always looking at what happens during the outburst. So the star came up, and in the B band, it was about 12th. At visual, it was about 10th magnitude, sort of plateaued and stayed there for on the order of a month, and then all of a sudden had this big outburst to 8th magnitude in B and 6th magnitude at V or visual. Dropped down, came back up, and then did kind of the normal nova fade. But at the time that it was doing this fade, it was getting extremely red. So this is where it starts getting into the L spectral class of star. And then for the next 2 years in this time scale, it basically sat down here, actually below the quiescent level of a single star. So basically something was obscuring the star that was um, uh, in an outburst. And so the idea is a shell of material was expanding and it was optically thick. And so you just didn't see down into it and be able to see the remaining star. Here are the images that were available before the outburst took place. And they're all from the Palomar Observatory Sky Survey place. And there were the POS-1 in the 1950s and the POS-2 in the 1980s. And you can see that the object basically didn't do a whole lot. It seemed to be a star that was pretty colorless, and it actually is a B-type star. And it looks, and based on spectra and everything else, the concept is that it actually was a pair of B stars. That was about the only plate material or imaging that we had prior to the outburst. Now, if you look at a typical nova, as typical as novae go, Nova Del 2013 is a good example. This is about 10 years after that outburst, and so we do have a decent amount of data. You can see that they go up to a peak, and then they come down in brightness, and then they just sort of fade away. One of the neat things to notice is that these are the R and I measurements, so red and sort of far red is what I would call it. And you notice that the I band measurements continue to fade. The B band measurements also continue to fade, but the V and the R band actually sort of are elevated above the others. And so what if you start looking at the spectra, what happens is that these guys here are looking basically at the continuum of the light coming from the star. And these guys have H alpha and oxygen 3 and several of the nebular emission lines in them. And so they stay bright. And so that's a typical thing that you see in a nova, is that at some point it sort of crosses over from being a star to being a star plus some shell around it that's being illuminated. And if you look at the full 10 years of the star since then, you can see that's basically what happens. The continuum or surface of the star continues to dim, and the filters that show the nebular emission lines also dim, but just not quite as quickly. And the quiescent level of the star is about 17th, so it's getting down there. If we had these measurements in more recent time, if you had amateurs that were able to observe down at 18th magnitude or something, you would probably see that we're basically back to quiescence for V838 Del. This is a spectrum of it near the peak of the outburst. And again, typical novae, you see H alpha, H beta, H gamma, etc. Basically hydrogen lines, very broad, that are sitting on top of the continuum. And then this is when it's in this nebular phase. You get H alpha, you get your oxygen 3, you get H beta. And so you just get a bunch of line emission is all you see, plus a continuum that's much fainter. All right, so getting back to V838 Mon then, here was that light curve again with a lot of data showing in here. If you notice, the peak of the outburst is very well covered by my photometry. But this is the stuff from the AVSO database. And as opposed to V838 Del, this is a decade earlier. And so there aren't as many CCD observers at that time. And so the amount of data is actually pretty sparse. You can see sort of structure during the outburst and then sort of quiescence down here with not a lot of other filter of information. This is about 2 years worth of data. The outbursting year, the year after, 2003. So let's look at the whole 20 years worth of data from this star. And this is what you get. So again, here's your outburst at the very beginning. And then here's year 2, year 3, year 4, year 5, et cetera, all the way out to year 20. And notice the difference between this and a standard novae. It's not fading. In fact, it's actually brightening up. So from the time that it was sort of at quiescence, V of 16 or something like that, it's now at 13th magnitude. So it's increased in brightness by 3 magnitudes over quiescence. Not only that, but all of the wavelengths are going up at about the same rate. So it's a very different object than a typical nova. Notice the coverage is actually pretty good in these last few years, again, because it's getting brighter, so the amateurs are more able to cover it. But there's also some structuring here. There's about a 300-day period that's showing up at all wavelengths in the light. So that's another feature of this that is different than a typical nova. Now here's a graph showing sort of the spectral evolution from the time that it was an outburst where you get your whopping H alpha to the sort of in-between time when the star was starting to fade. A little bit of H alpha, but really pretty featureless spectrum. And then when it got into its steep fade, all of a sudden you're getting into a very red star spectrum with lots of molecular lines, molecular band heads, excuse me. And then this is the current spectrum. So notice again, it's not a nebular spectrum. It's just a red star is all that you're seeing off of this. So it's, again, it's not the typical nova. So it's something interesting to follow. There's some data from various sources that have been around. This one, for example, there was a survey that was taking place only in the red band passes and for about 6 years. And this is the light curve from it. However, notice that the magnitude scale on here is reversed. That's why it looks like it's fading, but it really isn't. It's getting brighter. Again, you start seeing the structure, sort of a pulsation that's a 300-day period. Assassin is another survey that monitors the entire sky. Here's its data, not terribly interesting. There is some data from Gaia, but it's primarily the parallax and proper motion. The photometric data really hasn't been released because the star is not recognized as Gaia as being a variable. So one of the interesting things is that the parallax is basically unmeasurable. So here's the parallax, but the error on the parallax is larger than the parallax itself. And so they really can't measure the parallax of the star, probably because it's not a star, it's an extended source. Same kind of thing with proper motion. I don't think I would believe this number, is that because it's not a star, it's really difficult to measure these things. So in summary, I just wanted to say that I think V838 Mon, even though it's 20 years after its outburst, is underobserved for its importance. You really ought to observe it. You really ought to maybe get spectra of it if you're capable of doing that at 13th magnitude. I think it's a highly interesting star and is telling us something. We just have to understand what that something is. It's continuing to increase in brightness. I haven't seen it change and turnover or anything like that. There's a lot of data that's sitting out in the literature from various observers, Linda Krauss and my data set, for example, that need to be added to the light curve potentially at the AVSO so that people have a full light curve of the star and can follow it. For instance, I have 483 nights of data from Howard Pond that have not been analyzed and need to be added to the AID. And as I mentioned, there's sort of a half dozen other members of this luminous red variable class. And some of these can be monitored now, they're still bright. And others, if we just continue to monitor novae and keep looking for other examples of this particular peculiar nova type, then we can monitor those as well and try to understand what the similarities are of the members of that class and how they differ from typical Nova. So that's all I really have to say. There's a whole bunch of references, and I'll go ahead and page through these just so that they show up in the recording. And you ought to take a look at these because some of those are really interesting papers. Okay, so that's it. Let me see if I can stop share here.
Okay, thank you, Arne. That was interesting. I've heard of that particular star, and I've seen it on the front cover of a book on my bookshelf here, but I had not considered observing. I thought it was sort of done and dusted and all done, but clearly we still have a lot to understand. So what sort of cadence should we be doing? Every few weeks or more frequently than that, observing it?
Well, if it does have a 300-day period, my rule of thumb is that you want to have sort of a 1% resolution of that kind of variation. And so I'd say every 3 days to a week or something like that is kind of the cadence that I would observe. Nobody, as far as I know, has done any high-speed photometry of it in the sense of looking for a rotational speed or something like that of the star. Mostly because I don't know what we're actually looking at right now. Are we still looking at just the expanding dust shell from the star that's being heated up even more, or are we actually starting to see some underlying star, in which case you might want to see whether or not it's rotating. So it might be of interest to do a time series of it at higher cadence. But certainly, monitoring it once or twice a week, I think would be a good starting point. Okay. And the thing is that, the light echo is gone, but the star itself is still pretty interesting. But boy, that light echo sure got around. I mean, it's on coffee mugs and books and everything else. So it's been really fun to be part of that whole process. Okay.
Do we have questions from anyone else here? If not, Jeff, unmute yourself, mate.
Yep. Can I just ask? I noticed that on the early images from March the 10th, there appear to be diffraction spikes associated with something very close to your target, but it's actually even then it was an extended source. So I'm thinking that maybe that was coincidental. There's something else that was causing the diffraction spikes. But
okay, so you're talking about the. So you want to look at the early images?
One of your first slides.
Yeah. Okay. So. So probably not that one because there's no diffraction spike.
Well, there appears to be for March the 10th.
Oh, you mean in here?
Yes.
Yeah. That's coming from the star itself. It's a combination of it's coming from the star itself, but it's partly is just the stretch. If you notice this line out here, let me get the pointer again. Sorry. This line, this direction, is actually an artifact of the CCD detector, in the sense the star is too bright, and so you're actually getting a blooming that comes off in this direction. And then these other things, this one here and this one here, are just typical diffraction spikes because the star is so bright. The idea here was that I wanted to see what the light echo was doing, and so I was overexposing the star in order to be able to get to the light echo.
Okay, thanks.
So is that, yeah. And then of course with HST, it's just the typical diffraction spikes. And then here, again, you can see the diffraction spikes of this particular, this is a different telescope than I was using for the other one, but you can still see them, you know, pretty typical
Yeah, you can see it
imagery,
on
except for
other
that
stars,
weirdness.
but I was thinking that this target was an extended source, so I was a bit surprised to see. You know, you even consider maybe it was a multiple source or something like
Right.
that.
Yeah. So that's just because it's so overexposed. It looks like it's coming from the extended source, but it's not. It's coming from the underlying star.
Okay, thanks.
Thank you.
Thanks, Jeff. One other quick question: that 300-day oscillation period.
Yeah.
If I remember correctly, you mentioned that it might be a binary. Is that right? Do you think it might be?
Well, yeah. I mean, the concept was that because of the spectra, that it looked like it was a pair of stars. Because when one of them, you could actually see the second B star for quite a while after the first one went into outburst and was covered by the shell of material, the shell of dust. You could actually still see a B star spectrum. So the idea is that it had to be a binary. But you don't see either B star now.
Right.
It's just all red. So the second B star, if it were an actual member, in the sense that the two were gravitationally bound, the second B star must then be inside of the shell of expanding material.
Okay. So would this be sort of analogous to the Eta Carina situation with the homunculus around that?
It could be, but this is a very dense material because it's obscuring the star. You can't see the B star at all. So it's thick, and it's really thick. So it's probably similar in a way, but it's you know, you're talking probably orders of magnitude more material, at least in close to the star.
Okay. All right. Intriguing. We might let you go past your bedtime, I think I heard you say earlier. Thank you very much, Arne, and we'll see you next week for the closing presentation at session 3 as well.